Hi everyone, welcome to Unit 23 of online course on probability distribution. In the last session, we have defined geometric distribution and derived its mean, variance, probability generative function, moment generative function, cumulative generative function, etc. And also we derived moments of geometric distribution using the moment generative function, and of course using the cumulative generative function we derived its cumulants also. And in this session we are going to introduce or describe a very interesting property of the geometric distribution, namely lack of memory property or memory-less property of the distribution. Lack of memory property that satisfies by a discrete random variable having integral values, positive integral values. The only distribution is geometric distribution. We will prove that concept also in the later stage of this session. And what do you mean by lack of memory property? See, considering an event and that has not occurred before time j, that is x greater or equal to j, and suppose y is our additional time required. So, y is equal to x minus j, additional time needed for the occurrence of the event success E. And then probability of y is equal to x minus j greater or equal to k, given x greater or equal to j is equal to probability of x greater or equal to k, which implies that the additional time to wait for a success has the same distribution as initial time to wait. And this property is known as lack of memory property. So, how do you prove this lack of memory property for the geometric distribution? So, once again, the probability of y is equal to x minus j greater or equal to k, that is probability of x greater or equal to j plus k, y is equal to x minus j greater or equal to k, that means x greater or equal to j plus k. Given x greater or equal to j is equal to probability of x greater or equal to k, that means the additional time to wait for a success in a sequence of Bernoulli trials, if we are performing the Bernoulli sequence of trials until a success is obtained, has the same distribution as initial time to wait. So, let us prove this property for the geometric distribution. We have to prove probability of x greater or equal to j plus k given x greater or equal to j is equal to probability of x greater or equal to k. Remember, x is the number of failures preceding the first success in a Bernoulli sequence of trials with the probability of success p. So, remember this. So, x is the number of failures preceding the first success in a sequence of Bernoulli trials, and in that Bernoulli trials the probability of getting a success is p. And so, if it is the probability of x is equal to some x, that is the probability mass function is q power x into p, where x is equal to 0, 1, 2, etc. Already we have given this probability mass function. probability of x is equal to x is equal to q power x into p, where x is equal to 0, 1, 2, 3, etc. and p and q satisfies p plus q is equal to 1 equation. And consider the left hand side of that expression, that is probability of x greater than or equal to j plus k given x greater than or equal to j. This conditional probability you consider. By the definition of the conditional probability, this is same as probability of x greater than or equal to j plus k intersection x greater than or equal to j divided by probability of x greater than or equal to j. So, using the definition of the conditional probability, we can write probability of x greater than or equal to j plus k given x greater than or equal to j is probability of x greater than or equal to j plus k intersection x greater than or equal to j divided by probability of x greater than or equal to j. And the numerator value, see, it is the intersection of two events, that is one is x greater than or equal to j, that is this part, and another is x greater than or equal to j plus k, that is this part. So, the intersection means this region. So, this is nothing but probability of x greater than or equal to j plus k. The numerator is remains probability of x greater than or equal to j plus k divided by probability of x greater than or equal to j. And using the probability mass function, this is same as sigma x is equal to j plus k to infinity. Probability of x is equal to x, we have the q power x into p, because already we have the geometric distribution mass function, that is q power x into p. That divided by this expression, that is sigma x is equal to j to infinity q power x into p. Again, simplifying this expression, this is equal to the last step, we have sigma j plus k to infinity q power x into p divided by sigma j to infinity q power x into p. This is same as, see, q power j plus k into 1 plus q square plus etc. When we expand the numerator, the p will be is a common factor in the numerator and denominator, that will be cancelled. And substituting x is equal to j plus k to infinity, the values q power j plus k is common factor, so you take outside, so we can write like this divided by, similarly here it is q power j into 1 plus q square plus etc. or that is equal to q power k. So, the left hand side of that conditional probability expression, the left hand side expression, that is the conditional probability expression, is q power k. And what is q power k? Q power k is actually probability of x greater than or equal to k for a geometric distribution y, because probability of x greater than or equal to k for a geometric distribution is equal to sigma x is equal to k to infinity q power x into p, and that is equal to p into q power k plus q power k plus 1 plus etc., or that is equal to p power k, p into q power k 1 minus q power minus 1, or that is equal to q power k, p into q power k divided by 1 minus q power is p, so divided by p, that is q power k. So, for a geometric distribution, probability of x greater than or equal to k is nothing but q power k. So, what we have established, we have established that probability of x greater or equal to j plus k given x greater or equal to j is nothing but probability of x greater or equal to j if x is a geometric random variable with the parameter p. And this property we call it as the memoryless property or lack of memory property of the distribution. So, when we have considering the lack of memory property, we have j trials without a success. Okay? So, x greater or equal to j, that means we have j trials without a success, and the probability that we will have to wait until trial j plus k or more to experience a success. We are actually performing the Bernoulli trials until a success is obtained. So, we will have to wait until trial j plus k or more to experience a success is same as the probability of starting at 0 from the initial point and waiting until trial k or more to experience a success. So, and this is known as actually, if we are considering the geometric distribution, geometric random variable, suppose an event E occur anytime first trial or second trial or third trial, etc. And the occurrence time, that is waiting time we call, x has a geometric distribution with the parameter p, and it represents how long one has to wait for a success in terms of number of failures. So, if x has a geometric distribution with the parameter p, that x represents how long one has to wait for a success in terms of number of failures. And by lack of memory property, a random variable x that has a geometric distribution and usually referred as a discrete waiting time random variable, that discrete waiting time random variable satisfies lack of memory property. So, this is a very interesting property of the geometric distribution. Now, the question is, so already we have proved this. Now the question is, suppose x is a discrete random variable having integral values, positive integral values 0, 1, 2, 3, etc. And if it satisfies this property, that is lack of memory property, whether you can conclude that that is a geometric random variable. So, that is the very important result. That is, if x is a non-negative integral valued random variable, then and satisfying lack of memory property, whether you can prove that x is a geometric random variable. Of course. So, that is a result. If x is a non-negative integral valued random variable satisfies the lack of memory property, this probability statement, then x should be a geometric random variable. That is, in the family of discrete random variable having integral values, non-negative integral values, only the geometric random variable satisfies the lack of memory property. Okay. So, how do you prove this one? So, very interesting property, that is, suppose x is a non-negative integral valued random variable, non-negative integral valued random variable. That is 0, 1, 2, 3, etc. are the possible values. Suppose x is given like this. Also, you are given that probability of x greater or equal to j plus k given x greater or equal to j is equal to probability of x greater or equal to k. That is, we call this property as lack of memory property. So, these are given to you. Now, the question is, can you prove x is a geometry random variable? X is geometry. You have to prove x is a geometric random variable with a parameter some p. So, the question is, our aim is to prove this x is a geometric random variable. And to prove this, we consider, so let we denote pk as probability of x is equal to some k, where k is equal to, of course, k is equal to, we have already given that is non-negative integral values. So, k have the values 0, 1, 2, 3. So, let us give the notation pk as probability of x is equal to k. Also, you give another value as, suppose, let us make qk, that is not the usual way of representation. Let me take this as qk is equal to probability of x greater or equal to k. So, let us consider pk as probability of x is equal to k, and another quantity qk is equal to probability of x greater or equal to k. You are given that probability of x greater or equal to j plus k given x greater or equal to j is equal to probability of x greater or equal to k. This is given to you. And now, this statement, use the conditional probability concept, we can write this is x greater or equal to j plus k, x greater or equal to j, intersection of that two events. This is probability of x greater or equal to j is equal to probability of x greater or equal to k. So, the statement, the probability statement can be written using the concept of conditional probability like this. This is x greater or equal to j plus k, intersection x greater or equal to j. And we know this x greater or equal to j plus k, intersection x greater or equal to j is nothing but probability of x greater or equal to j plus k. That divided by probability of x greater or equal to j is equal to probability of x greater or equal to k. So, from the statement we have this. Now, look the notation. Probability of x greater or equal to j plus k, probability of x greater or equal to k, we have the qk. So, this can be written as actually qj plus k. Okay. This is qj plus k, and that divided by qj is equal to qk. So, we have, on the basis of the notation, we have qj plus k divided by qj is equal to qk. So, we have already proved qj plus k is equal to qj into qk. From the last expression, we have this qj plus k is equal to qj into qk. And let us take k is equal to 1. What is the modification? So, qj plus k, sorry, j plus 1 is equal to qj into q1. That is by taking k is equal to 1. And let us consider what is q1 actually. We have qk is equal to probability of x greater or equal to k. That is our notation. So, what is q1? Q1 is equal to probability of x greater than or equal to 1. And what is probability of x greater than or equal to 1 means? It is probability of x is equal to 1 plus probability of x is equal to 2 plus probability of x is equal to 3, etc. Or that is 1 minus probability of x is equal to 0. Because we have already given that x is a non-negative integral value random variable. So, by taking the complement, we have this one. This is equal to, we have 1 minus, we have the notation this 1 minus P0, because we have probability of x is equal to k, we have the notation Pk. So, probability of x is equal to 0 is 1 minus P0. Substitute here, this is 1 minus P0 into Qj. So, we have Qj plus 1 is equal to 1 minus P0 Qj. Or let me take this as Qj is equal to 1 minus P0 Qj minus 1 by j. So, this expression can be written like this. And this is actually, by repeating the procedure, we can prove this 1 minus P0. This is 1 minus P0 into Qj minus 2, that way you can write. Continuing the procedure, finally we can write this is 1 minus P0 power j into Q0. So, that is 1 minus P0, 1 minus P0, Qj minus 2. Next one is 1 minus P0, 1 minus P0, 1 minus P0, Qj minus 3, etc. So, 1 minus P0 jth power into Q0. So, that is, we have established that Qj is equal to 1 minus P0 power j into Q0. And what is Q0? See, just look, Q0, Qk is probability of x greater than or equal to k. So, what is Q0? Q0 is probability of x greater than or equal to 0. That means it is the totality, because x is having the values non-negative integral values. So, this is equal to 1. So, what is this? 1 minus P0 power j. Now, consider the Pk. What is Pk? Our probability of x is equal to k. And how do you get this Pk in terms of Qk? This is nothing but it is Qk minus Qk plus 1. Why? Because Qk is probability of x greater than or equal to k, and Qk plus 1 is probability of x greater than or equal to k plus 1. Subtracting these two values, you will have the probability of x is equal to k. Substitute the values from here. It is 1 minus P0 power, it is k, Qk, minus 1 minus P0 power k plus 1. And that is simplifying. 1 minus P0 is common, and having the value 1 minus P0. So, our Pk is equal to 1 minus P0 into 1 minus P0, or that is, finally we have Pk is equal to 1 minus P0 into, this is actually P0. Sorry, this is 1 minus P0 power k. 1 minus P0 power k is taken outside. So, 1 minus P0 power k into P0. So, what we establish, that is probability of x is equal to k is equal to, this is some you let me take this as q. So, q power k into this is p, where q is our 1 minus p naught and p is our p naught. So, this is nothing but the probability mass function of a geometric random variable. So, that is, whenever you are given x as a non-negative integral valued discrete random variable that satisfying lack of memory property, then we can establish that x is nothing but a geometric random variable. So, this is the way we are proving the lack of memory property, proving that whenever a discrete random variable, discrete integral valued, positive valued random variable satisfying lack of memory property, then that x is a geometric random variable. So, the proof is we establish. So, this is the result. So, these are the expressions I have already explained to you, that we have the probability of x is equal to k as pk, and we define the qk like this, and you are given that x random variable satisfying the lack of memory property. So, that is probability of x greater than or equal to j plus k given x greater than or equal to j, that is equal to probability of x greater than or equal to k. So, on the basis of the argument that is already I explained, we establish that x is a geometric random variable. So, these are the concepts behind the lack of memory property. That is, in the session we established that we have the geometric random variable, and for that geometric random variable we established a very interesting property, lack of memory property, and after that we have established that whenever x is a discrete non-negative integral valued random variable satisfying that criteria, the lack of memory property criteria, then we can establish that x is a geometric random variable. These are all related with the geometric random variable, and we will discuss further problems regarding the geometric random variable in the next session. So, thank you for listening this session. Thank you once again.